Hello everyone, welcome to topic 7.1, Introduction to Equilibrium. By the end of this, you should be able to explain the relationship between the occurrence of reversible chemical or physical processes and the establishment of equilibrium to experimental observations. Many chemical reactions do not proceed in only one direction, from reactants to products. Consider a sealed bottle of water. The water can evaporate and condense within that bottle. We call reactions that can go in either direction reversible and use a double-sided arrow to indicate a single instead of a single directional arrow to describe them, because they go in both directions. There are many types of reversible reactions that include evaporation and condensation of water, absorption and desorption of gas by a solid, dissolution or precipitation, proton transfer in an acid-base reaction, and the transfer of electrons in a redox reaction. So all of these proceed in both the forward and reverse direction, and that is what equilibrium is. In a reaction that is reversible, it will eventually reach a state of dynamic equilibrium. Equilibrium is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. This does not mean that the amounts of the reactants and products are equal. Okay, it's equilibrium, dynamic equilibrium, not concentrations are equal. When the rates of the forward and reverse reactions are equal, there's no net change to the amount of products and reactants. So the rates are equal, but not the products. Okay, so how fast the reaction is making products is equal to how fast the reaction is making reactants. So the rate that the reactants are being used up is the same rate that the products are being used up. So it looks like the total amounts of products and reactants are not changing, but in all actuality they are. The equilibrium is dynamic, which means that the reactants and products are constantly being formed, but at the same rate. So dynamic meaning you're still reacting stuff, but equilibrium brings this idea that it's happening at the same rate. So things are being made at the same rate that they are being consumed. We can graph changes to the concentration of reactants and products as a reaction proceeds to equilibrium. You can see that the reactants and products change rapidly at the bottom in the graph to the right, and then the rate of the reaction decreases until the reaction reaches equilibrium, where we see that the rate doesn't change. It's still reacting, but the rate is not changing. Okay. When the reaction reaches equilibrium, there's no change to the amount of reactants and products. Okay, so let's look at how we can apply this. So given the reaction here, the reaction starts with only 1 atmosphere of A, and that's pressure. Remember, ATM is atmospheres, and that's a measure of pressure for gases. 1 atmosphere pressure for A, 1 atmosphere pressure for B, and there's no C or D in the flask. Sketch a graph to show the reaction as it proceeds to equilibrium. Upon reaching equilibrium, there is 0.08 atmospheres of A. So we need to label, and so we could label every point. Need to change that to a pen. Every 0.2 or 0.1. So 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so all the way to just above 1. So we know that A and B both start at 1, and that A decreases to 0.8. Well, if we're keeping the same stoichiometric ratio, that means B has to decrease to 0.6 because twice as much is used due to the stoichiometry. So eventually, it should end up decreasing to these lines. So this would be A, and it should decrease rapidly, and then flatten out, and then decrease rapidly, and then flatten out. And then, so this would be A, this would be our B, and then we have to draw C and D. Well, they're both in a 1-to-1 ratio, which should match the amount of change. So how much C and D we make should equal the amount of A we used, because they are in a 1-to-1 ratio. So I use 0.2 of A, so that means that I should eventually make 0.2 of C and D, and they all should come to equilibrium at the same time. Okay, and so that is our equilibrium point. So the lines should be straight after equilibrium is reached. If mine are kind of curving up, it's because I'm drawing this on my laptop, but they should be straight and have no slope, or the slope should be 0. And they should match the changes should match the stoichiometric ratio if we're given starting amounts and ending amounts. So let's look at this we do. So we're going to write an equilibrium reaction. So remember, that means that when we write the reaction this time, we're going to use this double-headed arrow for the following processes. So I want you to pause the video and try try all of these right now. So please pause the video now. Okay, so you should have gotten these 3 expressions. So for the first one, freezing melting means you're going from the solid to the liquid phase and back again. So we have to make sure for equilibrium expressions, this is very important, that we're using the states of matter, and we consistently use the states of matter. Then in B, the dissolution of the weak acid HCN, or cyanic acid. So when we see this one, we always start with this one, and it's going to split into its 2 separate ions. Because it's in a solution and it's ionizing, we still are all in aqueous states, so we make sure we keep that. But we split the hydrogen ion from the cyanide ion, because it's a dissolution reaction. Then the proton transfer between the weak base, HS minus, and the weak acid, H2PO4. So we have to remember that the acid gives up a proton, and that we're going to add that proton to the base. So the base is the proton acceptor, the acid is the proton donator. So we're going to take a proton and transfer it here, and we would get the reaction, or the products on the right. And we, for all of these, use a double-sided arrow because these are equilibrium reactions. Okay, using this information, please complete the You Do, check your work, and thank you for tuning in.